Today we will be discussing skewed thermodynamic geometry and optimal free energy estimation. Our goal will be to vary some control parameters as a function of time to drive a system between two states, both forwards and backwards. For the specific case of a Brownian particle in a harmonic potential, where we change the stiffness of the trap as our control parameter, the optimal protocol for getting the best estimate of the free energy in terms of precision is given by this blue curve here, and in terms of accuracy by this red curve here. And we will show that these perform significantly better than the naive, that is the linear protocol, driving the system between the two states. So these results are based on a near equilibrium approximation for the excess work. So the excess work is the average work that you do minus the free energy difference. Recall from the second law of thermodynamics that the excess work is always greater than or equal to 0. The excess work quantifies how much energy you waste in this process, and is a very important quantity in terms of determining the optimal protocols for getting the best free energy estimates. So in particular, in the near equilibrium regime, the excess work can be written in this form in terms of the Stokes friction tensor and the control parameter velocity. Here the indices I and j index different control parameters. For example, you could think about the stiffness of the trap, the center of the trap, as just a couple examples. Now our goal now is to find the protocol, lambda of t, where lambda are the control parameters, that minimizes this excess work, which will also help improve our free energy estimates. So within this approximation, it turns out finding the protocol that minimizes this contribution to the excess work is relatively straightforward and can be mapped onto a geometric framework. In particular, this is what's known as a Riemannian metric. The classic example of a Riemannian metric is moving on the surface of a sphere. So the minimum distance between 2 points, say here and here on the surface of a sphere, are given by these great circle lines. So in order to minimize the excess work, we're going to have to find the equivalent of these great circle lines within the Stokes friction metric. Now one key feature of a Riemannian metric is that the distance between these 2 points does not depend on what direction you go. So when you go forwards, the amount of excess work that you're going to get is going to be the same as when you go backwards. Now it turns out this is only true at this level of approximation, and it's going to be very important when we're looking at free energy estimation to account for the differences between the excess work when you go forwards and backwards. So it turns out you can write the next order contribution in a very similar form in terms of this supra-Stokes tensor and these control parameter velocities here. But what's completely different about this level of approximation is that rather than having the tensor contracted with the two of the control parameter velocities, that is the velocity squared, this goes as the velocity cubed. So now, when you go forwards and then go backwards, this contribution actually changes sign under time reversal because it goes as the cube of the velocity. Now this gives it a very different underlying geometric structure. So it sounds like some sort of weird exotic kind of geometry where the distances that you travel depend not only on where you're going, but in which direction you're traveling. Now it turns out this is a very natural thing that arises in navigation, and it's known as a Finslerian geometry. It actually arises quite naturally if you think about the surface of the Earth, rather than being a perfect sphere as having all these different air currents. So for example, if you imagine going from one point to another on the surface of the Earth, because you have all these different air currents that have a tendency to blow in one direction more than the other, the distance when you go in one direction is going to be a lot easier than going backwards, for example, depending on the different air currents. So what at first seemed like a very strange kind of geometry really arises quite naturally in the geometric framework. And even when you keep this level of approximation, there's still standard methods for finding ways to minimize this excess work, or just minimize this contribution to the excess work. Now that's all for multidimensional control. Turns out things are a lot simpler for one-dimensional control. In particular, you can show that for one-dimensional control, to minimize the contribution from this Stokes friction, you just go at a velocity that's proportional to 1 over the square root of this Stokes friction. So you go fast in regions of low friction and slow in regions of high friction. Very similarly, the contribution from the supra-Stokes tensor, that's this asymmetric contribution under time reversal, is minimized by going at a velocity that's proportional to 1 over the cube root of this supra-Stokes tensor. So once again, you want to go slow in regions of high superstokes, and fast in regions of low superstokes. And that is exactly how we get these different protocols I showed at the beginning. So the model system we're going to be looking at is what's known as a breathing harmonic trap, where we change the trap stiffness from some initial tightly confined state to some weakly confined state. And then we do this in both directions and use work measurements in both directions to compute the free energy difference. So for this particular model system, you can show that the optimal protocols, the ones that minimize these different contributions to the excess work, follow these different curves. In particular, the most precise estimate of your free energy difference, the one that minimizes the variance, is given by this blue curve, which minimizes the Stokes contribution. And then the most accurate, the one that minimizes the bias, is given by this red curve here and minimizes the contribution from the super Stokes. So now that we've calculated these protocols, we want to know how well do they perform. So first, we're going to look at the variance of your free energy estimate as a function of protocol duration. And keep in mind that large protocol duration corresponds to a slow protocol, which will be where our approximation is valid. So we have three different curves here. The black curve is the naive, blue is the precise, and red is the accurate. So those are the three different protocols that I showed before, where naive is the linear protocol. And what you can see is that if you go to a sufficiently large protocol duration, the precise and the accurate curves lie significantly below the naive, which implies that they have significantly lower variance. Exactly how much lower? Well, we can look at the ratio of the design to naive, design being the precise and accurate, and naive being that linear protocol, and see how much better you perform. And once again, if you look in the large protocol duration limit, what you can see is that these precise and accurate curves are actually roughly 4 times more precise, or have 4 times lower variance. Similarly, you can look at the bias as a function of protocol duration, and what we immediately observe is that, once again, for large protocol duration, the precise and the accurate curves lie significantly below the naive, which is the black curve. Exactly how much better do they perform? Well, we can once again look at the ratio, and you see that for large protocol duration, you can actually get 32 times more accurate of an estimate just by following a different path through control parameter space. Now, I just want to emphasize that for these, you don't actually need to go slower than the other protocols, you just follow a different path through control parameter space, and you get a much better estimate of your free energy estimate in terms of the variance as well as the bias. So in conclusion, we have new approximations for moments of the excess work, in particular in terms of the Stokes and super Stokes tensors, and that these approximations allow us to design protocols that reduce the bias and variance of free energy estimators.